Hello and welcome to Mr. Jackson's physics class. Today we're going to talk about parallel circuits. Parallel circuits are a little different from the series circuits and they can take a little bit more math, so just follow along and you'll pick it all up pretty quickly. Okay, so a parallel circuit, what it basically does is it offers different paths to the electricity or current. So let's draw one, okay? So here we have our battery, and here we have a circuit beginning to be drawn. But then what happens is you have a resistor, but then you have another resistor that is actually parallel to it. Okay, let me even put a third resistor in there, okay? So this would be considered a parallel circuit. Let's say each one of these is different. Let's just say this is 30 ohms. And this is 30 ohms, and this is 30 ohms. Okay, and let's give our battery, we'll give our battery 60 volts. Okay, so these would be a parallel. So what it means is, as the electricity is going down, the electricity can actually choose to keep going, or it can turn and go down through this resistor or this one. So it gives it three different paths because I put it in three resistors. If I only had two resistors, I have two different paths. So if it has different paths that are available to the current, that's what we consider to be a parallel circuit. Okay? So it's pretty simple how it looks and how it lays out. But let's talk about the math. When there are different paths for the current, then it can travel faster through a different path with less resistance. So if one of these was 10 ohms, then electricity would probably push through that path a lot faster, just like water finds the least resistance. So rivers always flow through areas that are easier to push through. So if there is one with less resistance, you'll find more of the current will flow through that less resistor. Okay? But I made all three of them equal in this case. So parallel circuits actually create less overall resistance than a series circuit. If these were all in series, it would add up to 90 ohms. We did that yesterday. It's 1 plus 2 plus 3, but that's not true for parallel. Parallel actually has a different formula. So let's find the equivalent, or we don't want to call it total because total means we would add them up. They actually call this resistance an equivalent resistance, and it is actually a fractional formula. And EQ is what they put. So what is it equivalent to? Because these, you'd be surprised what they add up to. So if I took three 30 ohm resistors and put them in this pattern, then what would happen is their overall, or what we usually consider a total resistance, which is now called an equivalent resistance, is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And so you'd have to add them up and then invert or flip the final answer. So let's do the problem here. It would be 1/30th plus 1/30th plus 1/30th. And with fractions that have the same denominator, you can add them together and get the same denominator. And then you add the tops up, so you get 3/30ths. But that equals 1 over R equivalent. So then what you do is you take both sides and you flip it. And so then you get R equivalent over 1 equals 30 over 3. And of course, 30 divided by 3 is 10 ohms. So what happens is when you put three 30 ohm resistors, you get a resistance that is equivalent to only 10 ohms. So actually, it creates less resistance to put resistors in this form. So resistors are put into circuits in different forms for different reasons. But if they do it in parallel, the overall resistance will be usually less than any one of those resistors. So this circuit only operates with about 10 ohms of resistance. Okay? This means the current in this situation, if these were all different numbers, would go through differently. But before I go on, I want to show you a circuit that has different resistors because you're going to have to be able to get better at this fraction math. And some people really struggle. So let's just give you a couple really quick examples of different resistances that are in different amounts. So let's take a circuit and let's draw them parallel. and let's give them different numbers, okay? And I want to show you how to do it a faster way. So let's give a 10 ohm, a 20 ohm, and a 30 ohm parallel circuit. Okay, we have our battery over here, of course. And then how would I find the math of that one? Well, I want to show you a quick method. Okay, so it would be 1 over R equivalent, which would be, because it's parallel, is equal to 1 over 10 plus 1 over 20 plus 1 over 30. And so now it complicates things a little bit. So you'd have to be good at fractions. So I'm going to do it the fast way. I know that these all go into 60, so I'm going to make a denominator of 60. 10 goes into 60 6 times. 20 goes into 60 3 times, and 30 goes into 60 2 times. And then if they all had 60 on the bottom, 60 over 6 over 60, 3 over 60, then I just have the same single answer at the bottom. Okay? And that equals 1 over R equivalent. Okay? And so if I want to get R on top, I would just flip both sides. So R equivalent for a resistor, that 6 plus 3 is 9 plus 2 is 11. I would get 60 over 11 because I flipped both things over. And if you take 60 and divide it by 11, you would get 5.45 ohms. 5.45 ohms. And that's less than any one of those. So it actually, put them in parallel, gives you less resistance. But if this is difficult for you to remember how to find the common denominator and add them together, I'm going to show you a quick, easy method. If you have, and sometimes in resistances, if you ever go into really hard problems, and we're not going to have these, but they might have a 5.5 resistor, a 10.5, and they might have decimal numbers. Then it gets really weird. So here's a fast, easy way. If you ever want to find these equivalents, and you got a bunch of fractions with different numbers on the bottom, you can do this really quick, and it works every single time. You multiply all the bottoms. So 10 times 20 times 30 is 6,000. So I'm going to put 6,000 on the bottom. Then what I'm going to do is I'm going to take the number that should go over here where the 10 was at. And remember, we have 3 numbers up here. One will go here, one will go there, and one will go there. What you do is you take the other 2 numbers. So here's the 10. So I'm going to take 20 times 30 and put it there. So 20 times 30 is 600. So this gets 600. Then where this one goes, I cover it, I multiply these two. So 10 times 30 is 300. And then where this one goes, I cover the 30 and I put these multiplied together. 10 times 20 is 200. So you're just multiplying the other 2 numbers. So if this one goes here, because of the plus sign, you multiply these 2 numbers. And then you go on, and then you just take all the numbers and you do the same thing we did up here. So 1 over R equivalent equals 600 plus 300 is 900 plus 200 is 1100 over 6,000. And then you flip everything over, okay, and you get REQ over 1, which is R equivalent, okay, and you get 6,000 over 1100. These zeros cancel out, so you get 60 divided by 11, 60 divided by 11, so you get the exact same number. Okay? And you can do that if you had 3 or 4 or 5 resistors. And the one would go there, you'd multiply all 4 of them together and put the answer there. And then that one, whatever numbers are left, you multiply. Or if it's just 2 numbers. So let's say it's 1 over 10 plus 1 over 20. You multiply the 2 bottoms. So you get 200, 10 times 20. And then you just say, okay, what this cover this goes here. So the 20's left over, so I put that there. Then I cover this one. Then the 10's left over, I put that there. I get 200 over 30 over 200, and then you flip the 2. So you can do it with 2 numbers, you can do it with 3 numbers, you can do it with 4 numbers, but that's a fast, easy way if finding common denominators are difficult for you. So I just wanted to show you that. Okay? So let's move on. So we have found the equivalent resistance of 330s. Okay? This means that the current is going to be, and if I have different numbers, then the current could be different through each branch. So like in series, we said I here and I here and I here and I here could be is different. No, it can be different everywhere. In this case, since I have 3 30s, it's not. It's going to be the same everywhere. But in case this was 10, 20, and 30, then if I put an ammeter in each branch would have a different reading. And so how would I find, so this means the current is different through each branch, okay? And especially if each branch has a different resistor. In this case, it would not because they're all 30. So how would we find the branch? Well, to do that, you'd have to find the entire current in the entire circuit first. And it's the same as the series one. It's V equals IR, and you take the battery, you find I in the circuit, okay? And that circuit would only be if the ammeter was here before it went all through all these, or if it was here, then it would not be in a branch, and these would give you the entire circuit amperage, okay? But these answers will be different when it's in the branch. So how do you find the complete entire circuit? You then just use R total, or equivalent in this case, because it's not really a total, we're not adding them up. And so if I wanted to know I circuit, here's your equation. I in the entire circuit, okay, would be V battery over R equivalent, okay? So this is the equation that you would use to find the entire circuit speed or current, or flow, I'm sorry. So here we go. The battery was 60, okay? And so it was 60 volts, and the R equivalent was 10 ohms. So 60 divided by 10 is 6 amps. Okay? 6 amps. So we have 6 amps. So the current entire circuit is 6 amps, which is different than in the branches. Okay? So let's find out, well, how would we calculate the one in the branches? Well, we just use V equals IR. Real simple. We're not going to change our math, but we're going to change the labels on our math. So we're going to go V equals IR. And we're going to get I by itself. So I in the branch is V divided by R. V is going to be the battery again. It still stays as the battery. But now we're going to put R in the branch that you're in. So if they're different numbers, you're going to get different answers for each branch. But in this case, I decided to use the same number. So the speed in this branch right here will be 60 volts divided by 30 ohms, which is going to be 2 amps. Okay? But the speed in the overall circuit is 6 amps. So that's different. Okay? And since this is 30, then I could find this one again, 60 divided by 30. But if it was 10, 20, and 60, it'd be 60 divided by 10, then 60 divided by 20, and then 60 divided by 30 if I was doing one that was each branch was different. Okay? So I got to be careful here. The branches do have different speeds, and to find that you have to use the branch resistance, okay? And you can find the speed in each individual branch. Well, the cool thing is when you find all the branches, they will add up to the total. So don't forget this. I total or circuit will be equal to I in branch 1 plus I in branch 2, and so on and so forth, will add up to the circuit ones. So I just want to point that out. So 2 plus 2 plus 2 will add up to 6. Okay? So all the branches, so I in the branches, I branch added together equals IC. Just so you guys know that. Okay? Now the last thing I want to point out is how do we calculate voltage drops? Voltage drops are when we put a voltmeter into a branch and try to figure out, well, how much does this particular branch use up? Well, it's a little different. Before we used the voltage, in the battery and everything like that. Well, but this is a little bit different. We're going to find the voltage drop in a particular branch or a particular resistor. Okay? So we're going to do it a little differently. What we're going to do here is we need to look at not the overall amperage. We need to figure out how fast is it being pushed through, because if it's going through slower, then the voltage is going to be different in that resistor, because remember, overall the resistance is less. So what we do to find voltage drops is we need to use what is the branch, not the total, but what is the branch speed times by that individual resistor in that branch that you're looking at. Okay? So if I wanted to find the individual voltage drop from this voltage one, okay, it would simply be V drop equals the branch, which is 2 amps, which is going through at 2 amps, okay? And in this branch, it has 30 ohms, so that's going to be 60 volts. It's going to be used up by that. And why is it 60 volts? Why is it using up 60 volts? That's the entire battery. Because if you look at it, if I cover my finger up on this, can't all of the actual voltage from the battery go right just to that one alone? If I broke these two off, couldn't it just go right into that one? So the truth is, each branch receives the entire voltage. Each branch receives the entire voltage of the battery. So these are a little different kind of problems, okay? So that's the notes you need. So maybe you need to do look at these. So you might want to do a screen print, okay? And then we need to give you the bottom one, which has the branch on it as well. So we have that there, and so you can write all those down, okay? So let's just do another one just to make sure we practice and we've done it good enough. So let's do a quick one with some different branches and do the math again really quick and make sure we're using it correctly. So this is a little bit trickier, and that's why it takes me a little bit longer. So let's go again, and let's give you one, let's say the battery. And let's say our battery in this case is, let's go with 40 volts. Okay? And we got a branch that has 10 ohms. We have a branch that has 20 ohms. And we have a branch that has 30 ohms. Okay? And so I can cheat. So I want to find, first of all, what's the total equivalent resistance for this whole thing. Remember, I got to do 1 over, so 1 over 10 plus 1 over 20 plus 1 over 30. And so remember, I've already done that for you. I did all the math 2 different ways, okay? And so let's just give you the answer. It's 5.45. So R equivalent equals 5.45 ohms, okay? But then I ask you, well, hey, what is the total circuit current? I would need to know the battery and the total equivalent. So all I would need to do to find the current that is in the entire circuit, that would be here. Okay? It would basically be the battery over the R equivalent, which is going to be 40 volts divided by 5.45 ohms. And so 40 divided by 5.45 is 7.339, so 7.34 amps. Okay? That's the entire circuit. And then when I add up all these branches currents, I should get to 7.34. Remember, I told you they're going to add up. So let's find the speed of the current through each branch. Okay? And we have branch with the 10 ohms. We have a branch with a 20 ohm, and we have a branch with a 30 ohm, if that makes more sense. Okay, well, here's my battery. It says I in the branch will be equal to the battery divided by the resistance in that branch. So I want to find what would be the speed through just this branch and then through this branch. And they're going to be different from this one, but these all three should add up to this number. Okay, so the math is here. It's going to be the battery divided by the branch resistance. So 40 volts, 40 volts, 40 volts, and I divide it by 10, 20, and 30. So I get 4 amps in this one. Remember, it's less resistance, so it should move faster, a little bit slower than the slowest of all. 40 divided by 20 is 2 amps. And then 40 divided by 30 is 1.33 amps. Okay? And if you add them all up, here's 4 and 2 is 6. That's 7.33 amps. 7.34. We have the same answer. So that would be the correct speeds or currents, through each different branch. Okay? And what if I want to know a voltage drop just around the 20? And so I put a voltmeter in here, and I wanted to find V drop, and I'm not going to do all three. And let's say I just wanted to do it in the 20. Then what I would do is I follow this rule where I want to use whatever the speed is in that branch times by the individual resistor. So in the 20 branch, it is 2 amps, and the individual resistor is 20 ohms, and 2 times 20 is 40 volts. So you end up getting the voltage drop. Since each one is individually attached to the battery, all three of them will always give you the same answer as the battery. So the voltage drop in a parallel will basically equal the V of the battery. So that's just a little offside note, which may help us do a lot more information. Okay? So there you go. That is the electricity calculations or current calculations, voltage resistance, and voltage drops for a parallel circuit. Thank you for joining me, and have a great day.